Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 3 of the lecture on regional skew. This is the 10th lecture in the course on statistical methods in hydrology. In our list of topics, we're on the Bulletin 17B and C guidelines for regional skew studies. Actually, in Bulletin 17C, we're not really recommended to do regional studies ourselves anymore. We're intending to wait for the USGS to perform more sophisticated studies throughout the United States. But in Bulletin 17B, there were recommendations for how to do a skew study, and I think it's worthwhile to see those methods to understand how the process is done. And there are times that we still need to do a skew study ourselves. So a procedure for developing generalized skews. So in Bulletin 17B, regional skews were actually called generalized skews, right? Now we almost always say regional skews. Okay, the procedure suggested using at least 40 stations or all stations within 100 square miles, but making sure to span a good range of watershed characteristics. They suggested screening out portions of records that are regulated. These days, we would say let's try to back out the regulation and produce an unregulated record instead. They suggested having at least 25 years or more of flows. Now that a lot of time has gone by, we would probably give a lot higher number than that, at least 50 or 60. And they said the station skew should reflect all the adjustments for low outliers and historical information and zero flows that are performed for Bulletin 17B. So pretty much do a Bulletin 17B analysis on each of the sites. Right. Once that's done, adjust the station skew for bias with one of these two equations. And then they had 3 methods that they recommended. The idea was to try all 3 methods and use the one that worked the best. So the first method was spatial, right, to create an isoline map. So plot your stations and your estimated skew coefficients on a map and draw isolines as well as possible, right? The mean square error in this estimate is going to be the computed value of skew that's plotted compared to the value of skew you would get by interpolating between your isolines, right? That would be the difference, and those differences would be squared and averaged. Right. The second method was developing prediction equations, right? Doing regression with watershed characteristics and climatic variables as the independent variables and the computed skew as the dependent variable, and develop a regression equation. And the mean square error in this approach would be the mean square error of regression that you're going to see on Thursday and Friday. The third method was just take the arithmetic mean of your stations. All right, just average them and use that value as the regional skew. The mean square error in that case is just going to be each station's difference from that average averaged. So the recommendation at that point was to adopt the method with the smallest mean square error. Okay, this slide just has the mean square errors that I just noted for each of the methods. Note the assumption that is behind the mean square error in each of these methods. It's actually accounting for only the spatial error in these methods for regionalizing, and it's assuming that the station skews that are being used are correct, right? It's not accounting for the error in the station skew estimates themselves. And this is where a lot of the improvements in the regional skew methods are going to make a big improvement for us. Right, so now I'm going to jump over to deriving the weighted skew formula, and then we'll get back to other methods for estimating regional skew in the next video. Right, so the weighting equation for regional skew, we talked about this kind of briefly in the Bulletin 17B and C lecture on flood frequency guidance. I'll do just a little bit more detail on it here. All right, so Bulletin 17B suggests that we weight the regional skew and the station skew to obtain some average value. So the regional skew is the value that we hope has been improved by regionalizing and bringing in information from other sites. And the station skew is going to be the value that is very specific to our watershed and the specific characteristics of our watershed, right? So we don't really want to use just one or the other. We want some reasonable combination of the two, right? So they suggested a weighted average of the regional skew and the station skew. So our task in terms of developing the weighting equation is to determine weights such that the weighted skew is unbiased and has a minimum variance, right? And so that's what I'm going to walk through. First, unbiasedness, right? We want the skew estimate by the weighted skew to be aiming at the right target. We want its expected value to be the right value. So if we've used the unbiasing equations on our skew estimates, then we can presume that the station skew and the regional skew are both unbiased. So then applying the expected value operator to the weighting equation, that operator lets us pull out constants such as these weights. And if the regional skew and station skew are unbiased, they're each equal to G. And so if capital G is skew, so that equation will be equal to G only when both weights sum up to 1. So for unbiasedness, we just need the weights to add to 1. And if we isolate the regional weight and substitute it back into the equation, we're here. Now, if we want to minimize the variance, first let's look at the variance, or S squared, of the weighted skew. So the variance operator also allows us to pull out constants, but then we square those values. So to minimize the variance, we're going to take the first derivative of the variance and set it equal to 0, right? So I'm not going to go through the algebra, but we get this expression for the weight to put on the station skew. And if we substitute this back in to the previous expression, we simplify down to here. Right now, I would like to see the variance of the station skew matched up with station skew. So I might redraw the equation this way. Right? Now we're seeing that the weight on each of these values is inversely proportional to its variance, right? So the bigger the error, the smaller the weight given to that parameter. And we had been working with mean square error as our metric for how good the estimate is. So now I've just replaced variance with mean square error in the equation. And this is the equations that we saw in Bulletin 17B and C, and that we saw in the lecture on that topic. So as I mentioned in that lecture, what we're going to see from the weighting equation is that when the regional skews are very accurate, it will be stronger as compared to the station skew. And if the station skews are less accurate, like for a smaller sample size, they're going to be weaker as compared to the regional skew, although a station with a longer record and therefore a more accurate skew estimate will be stronger compared to the regional skew, right? But we're really concerned with having an accurate estimate of the uncertainty in our regional skews and our station skews so that this weighting formula can work well. So just a few words about the development of the first national skew map. It was in 1974, developed by Hardison, and he wanted to develop a map for the entire United States because federal guidance was being developed, and he thought expecting analysts to do a regional skew analysis themselves was unlikely. Right, so he did a map with almost 1,500 stations, at least 25 years of record each. All the drainage areas were less than 1,000 square miles for this one. And he unbiased the skew coefficients by multiplying by 1.26, which is based on an average record length of 33. And then when the Bulletin 17 testing was done to compare the different probability distributions and whether or not to use regional information, Hardison's skew map was used for that study to represent the regional information. What's called Plate 1 in Bulletin 17B was an update of that study. It was also only based on data through 1973, but this time it had almost 3,000 stations, and the drainage areas went up to about 3,000 square miles. Just a quick view of the skew map so you recognize which map it is that I'm talking about. You might recognize an estimate that came from that map by the fact that the mean square error is 0.302 on average for the whole map, which gives a root mean square error of 0.55. So if you have an old study that had a regional skew whose value you don't necessarily recognize, but you see a mean square error of 0.302 in the weighting formula, then that skew probably came from the skew map. With Bulletin 17C, we're hoping to do a much better job than the skew map could do, and so our recommendation is not to use the skew map anymore. So that's the end of video number 3, and we'll be moving on to video number 4.